Okay, class, today we're going to talk, Today we're going to talk about friction. And we did a lab last class about friction, and we said that the friction is a force that acts in the opposite direction to movement. So it wants to stop our motion. Now we saw that with the block of wood. When we were trying to move it, there was a force acting against us. We had to work a little bit to get that box to move, or that piece of wood. Now, friction happens when two surfaces are touching each other. Okay, so in order for there to be friction, the two objects have to be touching. There can't be any space in between them. Now, what we see with friction, and a lot of you brought this up already, is that friction can cause heat. So take a second to rub your hands together, and you can feel that they're warming up. The same thing happens when this little boy is turning the piece of wood. It starts to heat up, and eventually he can start a fire this way. Now, the only problem with friction causing heat is that that's a form of energy that we can't use anymore. Okay? And so we're actually losing some of our energy in the process because it's creating heat. Now, the amount of friction depends on two things. The first, it depends on the type of surface. And we saw that again in lab. There was different numbers depending on if we were on the cement, the grass, or the track. The grass and the track had greater friction, and we can talk about that. It would be a good reason to have high friction on a track because we don't want our runners to fall down. We want them to get a good push off so that they can go faster. If we had runners run on, say, the tile floor in our classroom, it would be really slippery. They wouldn't have as much friction, so they wouldn't be able to push off of the surface as nicely, and they wouldn't run as fast as they do on a track. The second thing that changes the amount of friction is the force holding the surfaces together. If it's something heavy, there's a lot of force pushing downward on the surfaces, and the friction is going to be greater. We saw this when we changed in lab from the 500 gram weight to the 1,000 gram weight. Even in the exact same situation, the force we had to apply to get the object moving to overcome friction was greater when it had a heavier mass. That's why it's more difficult to move a desk with someone in it than to just push the desk across the classroom. It has a greater force holding the desk to the floor. Now, there are 4 types of friction that we're going to talk about, and we'll say examples for each type. The first type is static. And when you have static friction, the object isn't moving. So this is something we see every day. Okay? Us sitting in a chair, the papers sitting on the table. The net force for this one is 0, which means that we're balanced. So for this one, we'll write balanced. Sorry about the writing, you guys. Okay. Number 2 is sliding. So this is when something slides over a surface. This was our sliding force that we saw in lab when we were sliding that piece of wood over the track, over the grass, and over the cement. Now, because the motion is changing, our net force is not 0, and we're unbalanced. Go ahead and write unbalanced in your notes. Our third type is rolling, and this is going to be when something rolls over a surface. Usually the object will be round, like a ball, or like a wheel. For this one, again, the net force is not 0, so it's unbalanced. The motion is going to be changing. Finally, our last type is liquid. Some people also call this fluid. This is when you're moving through a liquid or a gas. So again, make a note there. Liquid or fluid is through a liquid or a gas, like the air. And again, for this, our net force is not 0. The motion is changing. Okay, let's take a second to review those. So we want to look at what type of friction each of these pictures represent. So we've got a guy pushing against the wall. Chances are the wall will not move. So what type of friction shows no movement, has a balanced force? Good. Okay, next we've got sliding. So these are two surfaces sliding past one another. Okay, and the little girl is riding down the hill. Her sled is sliding against the snow. Now think about it, you go faster when you're maybe on ice because there's less friction. So we can change the friction depending on the surface. The rolling, again, our hint here is wheels, so it's going to be the car. And then liquid, remember liquid can be a gas or a liquid, so this is going to be the bird flying through the air. Now we use the principles of friction in many places in our lives, and actually in the Olympics there is a group that uses friction to their benefit. Okay, so we're going to watch a short video on the science of curling. So if you haven't heard about curling before, this is kind of an interesting piece.
Explain this unusual sport for us. While scientists funded by the National Science Foundation explain how friction makes it all work. Curling, perhaps the most unusual sport in the Winter Olympics. A huge rock is thrust down a long sheet of ice. Two players sweep a path in front of it, guiding it to the center of the target, called the house. At the end of play, the team with the most points, the most rocks closer to the center, wins. Olympic bronze medal winner John Schuster is a lifelong curler.
My family is big into curling. I remember throwing, a rock at the curling club when I was, probably 6 or 8 years old.
Getting the curling stone from the start to the house is all physics, starting with a push-off against what's called the hack.
What you're able to do off of here is to position your foot to allow yourself to accelerate out of the hack with a curling rock. You can push out of this hack with a very high amount of force, and you know that it's going to transfer into the curling rock.
Then the sweepers move in.
This is like a synthetic material that has just a little bit of abrasiveness. Curling terminology as far as sweeping goes, it's anything that you could consider versions of yes. Yeah! But usually it's hurry and hard. You want them to push harder.
To help the stone go farther and straighter.
Back in the old days, people used to think when you swept in front of a rock, you cleared out snow and frost, and that allowed the rock to go further. Well, after we got the snow and frost elements removed when we moved indoors, all of a sudden you're sweeping a rock, and it's even affecting it more. It's going 15 feet further.
That's because sweeping wasn't just removing the snow and ice, it was reducing the friction between the stone and ice. The rapid back and forth of the sweeping generates heat.
It all just comes down to this, yeah. It comes down to this. They're warming that ice up, maybe enough to generate a meltwater film.
A meltwater layer that reduces friction creates a literal path of least resistance for the stone to glide on more easily. Friction is reduced even further by another characteristic of curling ice: bumps.
All the other ice sports have a smooth Zamboni surface, effectively. And curling requires that the surface of the ice be roughened.
Spraying water does the trick.
And then when it lands on the ice, it freezes up and forms these nice pebble-shaped bumps. And if you look at it, it looks like an orange peel. That kind of roughness is about the right texture. That gives us the surface we need.
But wouldn't the bumps, like mini speed bumps, just slow the stone down? Actually, it's the reverse. The points reduce the total ice surface the stone rides on. The less surface contact, the less friction. And there's another reason.
If we're on smooth, frozen Zamboni ice in an arena, if that's making a nice seal with the bottom of the stone, you're going to eventually form a vacuum as the stone moves across the ice, and it really